This section looks at the exclusive OR operator, along with some of its applications. We also examine the phenomenon of gate propagation delay and how it impacts design. So, without further ado, let's meet the exclusive OR operator. There is an exclusive OR operator indicated by a plus within a circle. This operator has the same semantics as the English word OR. It is equal to 1 when exactly one input variable is equal to 1. Exclusive NOR doesn't have its own symbol, but it is the complement of exclusive OR. This operator is true when both values are equal to 1, or when both values are equal to 0. It is also known as equivalence. Let's turn our attention back to exclusive OR. Here are some important identities that apply to exclusive OR. The exclusive OR operator is also commutative and associative. This means that we can evaluate 3 variable exclusive OR operations in any order we like. If you don't have a simulator that has access to an exclusive OR gate, you can construct one using the definition we discussed a few slides ago. I've done this on the right using circuit bursts. The 2-bit compare for equality or exclusive NOR is also fairly easy to construct. In fact, I used to use it as an exercise in CS150 back when we included an overview of the field as part of the CS150 course. Exclusive OR for more than 2 variables is replaced by the odd function, which means that it is true if only one variable is true or all 3 variables are true. In other words, an odd number of the variables need to be equal to 1. Here you can see an implementation of the 3-variable odd function that I created using circuit bursts. If we plot the odd function on a Karnaugh map, we get a very distinct pattern with minterms being a distance of 2 from each other. The minterms not marked with 1s are those minterms with an even number of 1s, so we can use those if we want to construct the even function. Propagation delay is the time required for a change in value of the signal to propagate from input to output. The operating speed of a circuit is inversely proportional to the longest propagation delays through the gates of the circuit. There are 3 types of propagation delay parameters: high to low, measured when the output goes from high to low; low to high, which is measured when the output goes from low to high; and propagation delay, which is the maximum high to low and low to high delays. There are 2 different models that are used for modeling gates during simulation. The first of these is transport delay. Here, a change in an output in response to the change of an input occurs after a specified propagation delay. The second model is inertial delay. This is similar to transport delay, except that if the input changes cause the output to change twice in an interval less than the rejection time, then the first of the 2 output changes does not occur. Rejection time is the specified value no longer than the propagation delay, and is often equal to the propagation delay. A circuit can behave very differently based on different delays, as you can see from this figure. Here you can see the transport delay and the second from the bottom, and the inertial delay as the very bottom. And so the values of the circuit are different depending on those 2 types of delays and which one you're simulating. Thanks for watching. Next time we'll look at hardware definition languages.